Hello and welcome back to Mikey's Flightdeck. Today I will show you how you can build this transponder panel for your Boeing 737-800 pedestal. For the beginning you will need the bottom and middle panel, two small on-off switches and a push button. For the TCAS knob, I had to design a combination of a 12-position rotary switch and a push button. And I came out with the idea that I could drill through this rotary switch here and then insert a metal shaft that can be I would call it the push axis of the button. And this axis can then push onto a tactile button below this rotary switch here. But how would I hold the push button in place under the rotary switch? And there I came out with this design here. I would call it a cage, where the push button is mounted on the bottom and then the rotary switch can be pushed in and hold in place with some screws, and then, so the idea, the axis will hit the button underneath, and so the rotary switch is still turnable and the button with the axis is pushable. So let's see if this design will work. First of all, we have to drill into the rotary switch here. The switch must be opened first to remove the spring and the two steel balls from the inside. Be careful when you open it, because the balls can jump out and you will never find them again. The spring must be cut in two shorter halves to make room for the new shaft to come inside. The coupling of the shaft to the button is made out of hot glue, and at this opportunity I repaired the arm ring of my dollar. The rotary switch and push button combination is built in now, but it wasn't as easy as it might look on the video. It worked out for me on my second try. So when you shorten the two sides of the spring, then make sure that you don't shorten it too much. Come closer to the length that you need, because when you cut away too much, then you won't let any detent be there in your rotary switch and you come out with something like a potentiometer. But this isn't what we want to come out with. So just shorten one ring of the spring after the other until you have the detent that you want for your rotary switch. The reason that I want to reduce a little bit the force that you need to turn this rotary switch is that I only will use a very small rotary knob on top of this rotary switch, and I think when the force to turn the switch is too big, then this small nub won't make it. And so reduce the length of the spring a little bit to reduce the force that you need to turn the switch. I hope this was clear now for you. You will have to prepare 2 dual rotary encoders. Again, I have designed a PCB, and this time this is the smallest one I have designed so far. All the components had to be gathered on a really small space, and so I used SMD components again for the LEDs here on this PCB. I have done this before on the ADF panel and this worked out great, and so I decided to do this again. But with one difference. On the PCB for the ADF panel I have placed the resistors directly, but there are some disadvantages in this method. The first one is always when I want to check which resistor I have used, I'm not able to come there to measure the resistor with a multimeter very easy. I have done this on my ADF panel, and I had to disassemble the panel from the pedestal and then go in there with a multimeter, and I was lucky enough that I could reach this resistor. Otherwise I would have had to dismount the backlighting panel and so on. So this is one thing that I don't want to have. And for all my other panels, I have placed the resistors directly on the Arduino. And so when I want to change any resistor for any LED on any panel, I can just disassemble the resistor here on my Arduino breakout board. And I wanted to come back to this method. And so keep in mind, for all of you who are building their panels after my plans, you have to add a resistor on the Arduino. So let's solder in the SMD LEDs and then all the other components. To prevent the LEDs from spreading their light, every sign sits in his own light box. Because there are so many components behind this panel, I used 30mm hex standoffs this time to bring a little bit more room between the backlighting plate and the panel.
The engraving on the push button is filled with wax.
After everything is assembled, we will have a look into the configuration in MobiFlight and ProSim and try to test all the functions. Again, like on my cargo fire panel, not everything is testable here, but we'll test at least if all the hardware and the electronic is working. In MobiFlight I have added some new devices to my Arduino K, and you can see them here. There are some button configurations which are mostly for the Rotary switch here and the other two switches. I have a 7-segment driver here. Again, you can see here my naming convention. I'm using a range of 3 pins because I'm using 3 pins, and so when I'm naming the cables, then I can use K42 up to K44 for naming these cables. And there are 4 rotary encoder devices for the 4 encoders that are built in the 2 dual rotary encoders. In ProSim you can find the needed configurations in config and configuration, and here in the combined config tab and in the navigation category. Down in this long list, down here you can find the TCAS and Transponder switches that we'll need here for this panel. If you want to make it easier for you, then use the search function to use for Transponder or TCAS, and then you will find all the configurations that you will need. Other configurations can be found here in the indicator tab, for example, all the LEDs, and in the numerical segment here, there you will find the configuration for the 7-segment display. I'm now diving into the specials of the configuration of this panel, but if you are new to the configuration in MobiFlight and ProSim, then watch my basic video where I go into every step in detail. I want to start with a test first this time and go into the details a little bit later. I have prepared running in the background. MobiFlight is running, and you can see the values are already coming like I'm supposing them. Let's start with the encoders first. So you can see I can increase the values, and the maximum is the number 7, then it falls back to 0, and so goes the other way. When I go below 0, it starts at 7 again, and this will be important later in the configuration. So this is the first segment. The second segment is editable, and the third one, there it works, and the last, here we have it. Now to the TCAS switch here. It is on TA now, and let's go to the left, and there you can see it is going into the position like I'm expecting it. When we want to test the buttons, then these aren't modeled here in ProSim displays, so we have to look into ProSim system to check the values. So let's go here in the navigation tab to the Transponder switch. There, the Transponder selector is on 1, like our switch here, and when I switch it to 2, then you can see here the value is changing to 2 and to 1 again. This is not visible here in the graphics. So, and the alternate source we can also check here. Up here we have the alternate source on 1, and now we go to 2. There it is changing to 2 and back to 1 again. The TCAS test button can be seen there, and when we push it,
it switches to pushed, and you can also see a reaction here on the display. This reaction, the fail string, isn't transmitted back to us. So until now I haven't found a value or a string that shows up this fail string, and so maybe I could model this with a configuration. I have decided not to model this here. Maybe I will find a solution for this in the future. But the test button is working, and so all the reaction on the MIP will also take place. Now the ident button here. Down here we have the exponder ident. It is on normal, and when I push the button, then you can see it goes to pushed. So this also works. And I have added a configuration and an FSUIPC offset, so it is transmitted to the simulator. And I haven't found a way to test this transponder fail light up here. When we have a look at ProSim systems, then we can see the exponder fail is always on. And I don't think this is right, because there isn't a reason for the transponder to fail now at the moment. But it is also not visualized here in the display tab. So I think it should be off, and I have put this beside. But we can test this light. I switch off the MobiFlight module for this moment and go to my configuration K45, which is this LED, go to test, and then you can see it is illuminated. A little bit too bright here. The 150 ohm resistor I have used here for this LED isn't not high enough, so I think I have to double this up to make it a little bit darker here. Okay, all the hardware so far is working. Let's have a look into some specials of this configuration here. One thing I want to show is the control of the ATC 1 and 2 mode. So I think these are these numbers here. When I turn the selected transponder to 2, then the 2 number is illuminated. I think there is a connection between these two functions here. And when I go back to 1, then it switches to 1. And this connection can be done without using an additional offset here. First of all, we have this ATC sign, and this is always on. And so I've thought, what can be the condition for this to be on? And this is the battery switch. So when this is on, then this light will be on. And I have done this here in my configuration 46. And I'm looking to the offset I'm using for the battery switch, and especially the battery switch off position. And then I'm making a comparison here. When the value is bigger than 0, which means my battery switch is in the off position, then I will set the value of this light here to 0, so it is off, and otherwise it is 1. So when the battery switch is in the on position, then this light goes on. This is all the magic behind this here. And now the change from the illuminated 1 to the illuminated 2 is modeled here in these two configurations, 47 and 48, which is my 1 and 2 light. And when we are looking to the 1 light, then I'm using another offset, and this is the offset I'm using for this transponder switch here, where I choose if I'm using number 1 or 2. And so I'm making again a comparison here, and when this value is bigger than 0, so the switch is in the 1 position, then I will set the value to 1. And because we are here in the 47 configuration, which is the 1 number, then this number is illuminated. Otherwise, the value is 0, so the number isn't illuminated. And the same comparison but in the other direction, I'm using in my configuration 48 for the number 2. I'm observing the same offset here and making a comparison, but this time the other way around. When it is bigger than 0, so the switch is in the 1 position, then it is off. So the number 2 is off. And otherwise, this means when my switch is in the 2 position, then it is illuminated. And so the 2 is illuminated. You can do this with an observer function here too, but with this method here, I'm not using an additional configuration line and I'm not using an additional offset. And so I think this will work here fine. And now let's come to the display and the 2 encoders. And here we are saving a lot of offsets. First of all, I have looked up in the FSUIPC offset documentation and have a look what I have found here. The offset 354 is used for the transponder setting, and we have 2 bytes here used, and these give us the 4 digits in binary coded decimal format, and it is readable and writable. And I can't say this often enough. If you have the possibility to save offsets, then do it. Use these FSUIPC offsets that are already there. So I have made a configuration with this offset here for my 7 segment displays, which are getting the value from it and showing it here on the displays. I have shown this in several videos in the past. And also for the 2 encoders, or better saying the 4 encoders, which they are, I'm not using any additional offset. Everything is managed in the configuration. So let's have a look into my input configuration for this. So here are the 4 configurations for every outer and inner encoder. Oh, and when we start with this encoder, 5251 it is called, this is the outer encoder of the left side here, which is responsible to control this first digit here. What I'm doing here is that I'm not looking how is the encoder moving, rotating in which direction and giving this information to program and so on, but I'm doing something with this information directly in the configuration. The first thing is that I have made a reference here, the Exponder var. You know this from past videos. I'm calling observer variables var when I'm doing something with it. I'm not only looking to the value for information, I'm using these configurations in other configurations so that I'm not deleting them. And in this Exponder var, I have the value of the exponder, of the 4-digit value. And I'm using the hashtag sign here as a reference. And when I'm now looking to the input tab, then I have to ensure that I only affect the first digit of this number, and when I'm moving it to the left, that I'm not going below 0, and when I'm moving it to the right, not above 7. And when it goes above 7, it has to fall back to 0, and the other way around, when it goes below 0, then it has to go up to 7 again, and only the first digit. So here you can see the offset of FSUIPC we want to use, and into this offset everything is written what comes out now here in my set value function. So now how do we affect only the first number? If my value is bigger or equal than 1000, so I know that not a 0 is the first digit, so then I can reduce the number by 1000 again, and this only affects the first digit. Otherwise, I have to add 7000 to the number. Again, it's a complete 1000er step, and so it only affects the first number. I'm not doing an on left fast. We only have to go through 7 steps, so this is fast enough. On right, when we increase the value, then if my number is smaller than 7,000, so I still can add 1,000, then I do this. Otherwise, I will subtract 7,000 from my value, and so I fall back to 0. That's all for the first digit. And in this way, it goes through all the digits. Let's have a look here to the second digit. Again, you can see I made a reference here, and here we are at my formula. It's a little bit different because now we can't just add 1,000. If my value modulo 1,000, so what does modulo 1,000 do? It divides the value as often as it is possible by 1,000, and the rest is given as a result. So I'm cutting away the first digit here, and in my case only 450 is the result that comes out here. So if this value is bigger or equal than 100, so I can still go lower, then I subtract 100 from my value. Otherwise, I'm already at a 0 value, then I'm adding 700 to it, and I'm jumping up to 700. On right, when I want to increase the values, you can see the same modulo operation in the front, and then if the value is smaller than 700, so I still can increase my value, then I add 100, and otherwise I'm reducing the value by 700. So, and this formula goes through all of the other configurations. You can see here we are acting in hundreds, and when we are looking to the configuration at the third display, for example, you can see we're adding tens and 70s, and the last one, there you can see we are only adding small values here. And this is the magic behind saving a lot of offsets. Let's build in this panel into the pedestal and finish another segment.
And here it is, built in at its final place. Again, one more segment finished and only 2 more to go here for the finished pedestal. One more word to the PCB here I have used. You have seen me using 4 7-segment displays, but I have built in 5. And this is because I have seen different versions of this panel out there in the web. Some have built a version with a leading F in front of these digits. I think when a failure is thrown or the test button is pushed or something like this. And to be more universal, I have built in 5 7-segment displays. So if you are building your panel after my plans, then you can configure it at your needs. And when I'm talking about my plans at the moment, you will find again a full set of files to cut out and engrave this panel, as well as the files for the PCB here and all the 3D print files for all the printed components in here. You will find this as a download in the member section of my website. And if you don't want to produce your own PCB, I have left over some from this panel here, and you can order them from me for a small fee. So I have to dive into the build process of the next section of the pedestal. And if you don't want to miss this upcoming episode, then subscribe to my channel to stay informed about any upcoming new video from me. And I hope we'll see you soon back on the flight deck.